Welcome back. So we were talking about the SVRG algorithm, and we mentioned that in a lot of scenarios in deep learning where the data size is very, very large, SVRG may not necessarily be better than SGD. Our analysis was based on the oracle complexity, something that is like theoretical in nature. So one may ask, maybe this theoretical reason is not enough to exclude SVRG from the set of our optimization algorithms for deep learning. But unfortunately, there are other shortcomings of SVRG-based methods that I'm going to talk briefly in this lecture. And at the same time, we're going to talk about some solutions on how to mitigate these shortcomings. Okay. So the idea is that basically SVRG is very actually useful for simple machine learning problems. Like for instance, solving a linear regression problem, solving a logistic regression problem, things of that nature that we talked about before, right? So very, very simple, where we are not necessarily using all of these heuristics and techniques we've talked about before, such as normalization methods, dropout, and also data augmentation, okay? Because in practice, when we are training deep learning models, we are using these heuristics and techniques, that's where the issue arises. SVRG may lose its effectiveness. In particular, this control variance idea that we use for variance deduction is going to lose its effectiveness. Okay? So this is a plot that I'm showing from one of the suggested reading materials, which basically shows the ratio of the variance of SVRG and the variance of stochastic gradient descent, calculated using different portions of basically data, for instance, 2%, 11%, 33%, etc. Okay, but those numbers don't matter as much. What matters is that what these plots show is that for different models, let's consider a small ResNet and a very large ResNet models. The larger the model is, the higher the likelihood of losing variance reduction property. So note that this shaded area here and here denotes the increase in variance, such that SVRG, a method that is using variance reduction techniques based on control variant, in fact has a higher variance than SGD. Okay, this is highly undesirable. Okay, so this shows that as your model becomes larger, you may actually lose the variance reduction property. And I should also mention that in training these models, these techniques such as normalization, dropout, and data augmentation have been utilized. Okay. So yeah, this basically shows that the variance could actually increase. Also, more or less, as you're training the model, there is basically an increase in the variance. Okay, for instance, here the variance is small, but as you're training, the variance is going to go up. However, when you are reducing the step size at 150 epochs, then we see a reduction in the variance. So using learning rate tuning strategies that we've talked about before, such as exponential decay, etc., could actually help with mitigating this increase in the variance problem. Okay, but what's the source of the issue? So I want to argue that the issue can be attributed to the assumption that we made, right? On the fact that we assume the loss function has a finite sum structure. The issue also can be attributed to the fact that the SVRG algorithm is an epoch-based method, meaning that we only update the reference point once in a while, such that the reference, the parameters, when we are updating them, they're going to update so rapidly such that the reference is not going to be a very good reference anymore in the context of deep learning. Okay, that's why we may see an increase in the variance. Okay, but this is actually a very subtle point. I would say that why we don't have this finite sum structure don't we have a finite number of data points? Okay, so if I have 1 billion data points, still a finite number, right? And I'm still minimizing the average loss. So this is still something that I'm minimizing. Why is not a finite sum? Okay, and this goes back to the fact that we are using these quote-unquote randomized techniques such as normalization, dropout, and data augmentation, which means that effectively we don't have a finite sum structure. Okay, so let rho denote the randomness due to normalization. Again, remember, batch normalization is a randomized operator because it depends on the batch that you are processing. Dropout, again, randomized. You flip a coin with some probability and then you sort of deactivate some of the neurons. Data augmentation, something we haven't talked about. It's nothing complicated. We will talk about it in briefly, but that basically means that in addition to processing the data, you will also process a random transformation of the data. Okay, so therefore, let's denote this source of randomness due to these techniques we are using. Now, effectively, what we are minimizing is actually this loss. So the loss of each sample itself is a stochastic function. Okay, it not only depends on basically the parameter W and that specific sample, but it also depends on this source of randomness rho. Okay, such that if I again give you the same W, give you the same sample, every time you're going to experience a different loss. Depending on, for instance, what is the batch, okay? What is the realization of the dropout method? What is the realization of the random transformation in data augmentation, okay? And this is something that is not accounted in the SVRG method. That's why it's not going to be as effective in deep learning problems compared to simple machine learning problems. Okay, so let's talk about the data augmentation a little bit more. So in practice, due to reasons such as improving generalization and also improving the robustness of our model, we not only use a specific sample Z, for instance, this could be an image, but we also use its transformations in each iteration. Okay, so for instance, I have an image, and then I want to use that to let's say update my model. Okay, in addition to finding basically the stochastic gradient at this image, I take the image, I randomly transform it. Let's say I do some cropping, I do some random rotation, I flip it, okay, to make sure that my model is robust, okay? So, and we're going to use all of these transformations, let's say, in our training, okay? And in deep learning packages, typically this transformation is automated, such that when you process a given sample, let's say you selected the mini batch and an image is in this mini batch. Now that you want to calculate the gradient, there's this automated process that it also calculates the gradient at the random transformation of the image. Okay, so this is something that is automated, and there are lots of empirical evidence that data augmentation helps improving the generalization and robustness of our models. So this is something that we want to use in practice. Okay. All right. So now let's see whether there is any conflict with the SVRG method. Okay. So let's imagine that I'm using this specific image Z tilde in iteration T. Okay. Now, what was our update vector? The update vector is written here. Okay, so it's a stochastic gradient at WT and an image Z tilde plus the true gradient at the reference point minus the stochastic gradient at the reference point and Z tilde. Okay. All right. Also recall that this stochastic gradient, the true gradient is calculated outside an epoch, while this stochastic gradient is calculated inside an epoch due to the epoch-based structure of SVRG. Okay. All right. So, however, Z tilde is an image in our data set, which means that not only it affects these stochastic gradients that I've written in using orange color, but it also affects this true gradient that I've written in blue color. Okay. So, but I've processed Z tilde at 2 different times, which means that when I process it at 2 different times, I'm going to sample 2 different transformations. Okay. So in particular, Z tilde appears with transformation T1 in the orange terms, but with another transformation T2 in the blue terms. Okay. So this basically implies that there's going to be some estimation error due to bias and increased variance, such that, for instance, this term is not 0 on expectation anymore. Okay, so that's one reason SVRG might not be as effective as what the theory suggests. Okay, and that's why we observed, for instance, in the previous slide, that in some cases there was in fact an increase in variance as opposed to a decrease in variance. All right. So this plot actually shows this idea that take a look at the red curve. Okay. So here again we are seeing the variance of SVRG within an epoch, in particular within epoch 2 of training the LeanNet model on the CFAR10 dataset. As you can see here, when we are just starting the epoch, the variance is low, but as I'm progressing in the epoch, the variance starts to go up. Okay, this is again due to the fact that we're going to incur some estimation error because of the data augmentation procedure. Okay, so the authors actually propose a solution that somewhat mitigates this issue, and they call it transformation locking, meaning that they want to ensure when I process Z tilde, both inside and outside of the epoch, I use the same transformation. Okay, so you store the transformation, use outside of the epoch, and reuse it inside the epoch. Okay. This, as you can see here, this helps that we reduce the variance, but nonetheless, as we are progressing inside an epoch, the variance starts to go up. And this is natural because as I'm progressing, I'm updating W while my reference is fixed. Okay, so therefore the variance has to go up. All right. So now let's talk about 2 other approaches that we use when we train deep learning models. We've talked about them extensively: dropout and batch normalization. Okay, and let's talk about the conflict with SVRG. So the dropout issue is actually similar to data augmentation, as again, for instance, inside and outside of an epoch, we use different sparsity patterns. Okay. So therefore, we expect to be able to use a similar locking solution, meaning that if you use a sparsity pattern outside of the epoch, you save it, okay, and then reuse it inside of the epoch. And again, this to some extent helps with the variance increase, with the increase in the variance issue we talked about. Okay. Now, with the issue with the batch normalization is slightly more complicated, and it's actually twofold. First, let's talk about this stochastic gradient. That again is a component in our update vector. Okay, so this now actually depends on other samples because batch normalization basically normalizes the activations according to the statistics of the batch. Okay, so in particular, if I consider a specific image Z, this stochastic gradient after batch normalization or with batch normalization active, when the batch is B1, is not necessarily the stochastic gradient when the batch is B2. Okay, and again, the implication is that there's going to be some increased bias and variance in the SVRG estimator. Okay. Notably due to its epoch-based structure. Okay, so that's one issue. Another issue that we can mitigate to some extent is basically in terms of inference. Okay, so we've been talking about the training, but how about inference? if you recall, when we talked about batch normalization, we said that you use the statistics of batch in training, but you use the statistics of the entire data during inference. Okay, calculation of the statistics of the entire data is too costly. So basically, we try to estimate that on the fly as we were running the algorithm. Okay, using something like the following updates. Okay, so we basically aim to calculate the statistics of the entire data, which means the mean and variance or standard deviation, from the statistics we calculate for the mini batches. So, and it is a standard practice to use something like exponential moving average, meaning that your next estimator of the, for instance, the mean of activations according to the entire data is some parameter beta times the mean of the current mini batch plus 1 minus beta times your previous estimate. Okay, and a similar statement or similar estimator can be used for the variance. Okay, so the idea is that when you want to do this with SVRG, the default implementation in deep learning packages is not going to be compatible. Okay, because the reason is we are actually calculating the statistics at 2 different points. Okay, not only we calculate that at WT, but we also calculated at V sub E. Again, this goes back to the structure of the SVRG update rule that I have here. Let's take another look. Okay, so this depends on WT. This term, on the other hand, depends on VE, which means that in each iteration you have basically 2 different statistics. Okay, so what the author suggests is to use what they call batch reset, meaning that you should make sure that you're not using the statistics at the reference point in your calculation. Only use the statistics at the current model, which is WT. Okay. So there you go. These are some basically issues and incompatibilities of SVRG and when it comes to training deep learning models. We talked about some solutions here as well, but the point I want to make is that we may need to go through a lot of pain, right, to use SVRG. Okay, and this is something that people may not necessarily want to do. So despite the elegance of this idea of variance reduction and leveraging control variates, for the most part, SVRG is not as popular as, let's say, something like SGD with momentum when it comes to training deep learning models. We want to nonetheless see whether there is a principled way to sort of reduce the shortcomings of SVRG and perhaps come up with another method that is slightly more, or even more than slightly more, application friendly. And this is indeed the case, and we're going to talk about the different methods in the next lecture. I'll see you there.